In this series, we're going to create an amazing odometer effect that's not just limited to numbers, it works with strings and you can also combine them like so. In this first video, we will focus on building the numbers only version step by step, but if you're ready and want to create a string version as well, head over to our website GraphFix.net and you can grab the complete tutorial at a very small price. We will create this by using HTML, CSS and JavaScript, so starting off with an M abbreviation, we will add the basic HTML elements and then we will link our style sheet and our script. Remember to add a defer to our script, and what I do next is create the files by control and clicking. If you've created the files, you can skip this, but next we add a div with the class container, and inside that div we will add another div with the class container value. And inside that we will create a div with the class value div, and then we will use the $sign inside curly brackets to add numbers inside those divs and multiply it by 6 to get 6 divs. Then I will duplicate the container value div by using Alt Shift and arrow keys, or Option Shift and arrow keys if you're on Mac. And then what I do is renumber these so each container value is incremented by 1, and this is what we have right now. So next we will go to our CSS to style it. So we start off by adding box size and border box to our HTML, and then using the asterisk symbol and the before and after attribute, which selects everything, we do a box sizing of inherit, a margin of 0 and a padding of 0. Next we select the body and we give it a height of 100 VH or viewport height, a display of grid, and we set it to have a place content of center, a font size of 10 rem. Then for font family I always select the bottom option with Verdana, but this time I will also select Career New, which is a monospaced font. However, I will comment it out as we'll use it later. I will also do a font weight of bolder, and this is what we have displayed right now. Next we will select our container div and we will give it a display of flex. And now all the container values are displayed in a row. Next we will give our container div an overflow of hidden, but in order for it to work we need to set a height value to container value, and I will do 1.4 em, and in order for it to be consistent I will select value div and I will give it a height of inherit, which will copy the height of its parent element. And to make sure that it works, we will go to container value and set translate to 0 minus 100%, and as you can see we've moved the values up by 1 increment. So now let's animate this by doing add keyframes, and I'll give it a name animation, and we will start with 0%, curly brackets, and inside we will give it a translate of 0, and for 100% we will give it a translate of 0 for the x-axis and minus 500% for the y-axis. So now let's call the animation. So for the name I will put animation, I will do a duration of 2 seconds, then I will give it an easing of ease, a delay of 0 seconds, and I will set the fill mode to forwards. So now it looks like this. Next we will create the blurring effect, and to do so we have to first go to our HTML and create an SVG. I will minimize the container value divs and start writing the SVG at the end after the container div. So I'll give it a class of blur SVG and then a width of 1 and a height of 1, then I will set the version to 1.1, then I will set the XML namespace to this value. All of this is mandatory in order for the SVG to work. However, if you want to, you can copy these small bits of code from our website GraphFix.net. Next we will add the definitions tag by writing defs, and inside we will add the filter tag. It's really important to give it an ID. I'll give it the ID blur filter, and next we will add the filter tag FE Gaussian blur. I will give it the class of blur filter Gaussian. I will set the in to source graphic and the standard deviation to 0.20. And then we will apply the filter in CSS by setting filter to URL. Then inside the parentheses we will do hashtag for the ID we created, so hashtag blur filter, and as you can see now it looks like this. Now to understand how this works better, if we go to our blur tag down to standard deviation, the first number is the x-axis blur and the second is the y-axis blur. So as you can see, when we set the x value to 2 or 10, it appears to be more of an overall blur, whereas when we set it to y-axis only, we kind of get this motion blur effect. Next we need to animate the standard deviation values, however we cannot do that with CSS, so for now I will comment out the filter and the animation property. Now in order to animate standard deviation we need to use some maths, so I will explain it first, but if you want to you can skip to the coding part at this timestamp. Now basically what I mean by animating standard deviation is being able to ease in from one value to another, as that is what we've done for our translate property in CSS in the animation. However, we cannot animate or transition standard deviation in CSS, so we have to do it in JavaScript. We can replicate almost all using properties with cubic Beziers. We will work with values from 0 to 1, as we can then multiply later on in JavaScript. The first graph is a linear interpolation, while the rest and the following are all cubic Beziers. You can search cubic Beziers online and you'd be able to play around with different values and inputs. The cubic Beziers we will work with are only made up of 4 coordinates, this being one example. As you can see, the points are numbered as P0, P1, P2 and P3, and they go from the bottom point to its adjusting point. Then we move to the top adjusting point to the top point. Each point has its x and y value. Now here's the cubic Bezier equation factorized and expanded. Let's look at the factorized one for a second. As you can see, we start off with the point P of t. What this will be is the x value we want in order to find our y value in the graph. However, this means we will have to do the math to calculate the variable t in order for this to work. So let's go through an example. So first we pick our cubic Bezier coordinates and add 2 to all values. I believe adding 1 works as well, but just to be safe, we will use 2. The reason we do this is because if you look at the equation, using 0 would multiply t by 0 in the first line, which would remove many values that are necessary to find t. Next, we will select the distance from the x-axis, in this case 0.6, and we will add 2 to this value as well. And now we can substitute all the x values inside the equation. And after we calculate everything, we have 2.8t cubed minus 4.2t squared plus 2.4t minus 0.6 is equal to 0. And to find t, we can use the depressed cubic equation, which turns the cubic formula at the top into t cubed plus pt plus q is equal to 0. This is basically done for substituting x is equal to t minus b over 3a. And then with this, we also get the values of p and q in forms of a, b, c, and d. But before we use the depressed cubic equation, we need to make sure a is not 0, otherwise p and q would give infinite values if we sub in a as 0. If a is 0, then it becomes a quadratic equation. Secondly, we need to make sure that both a and b are not equal to 0, and if they are, we solve as a linear equation where ax plus b equals to 0. And thirdly, we need to make sure that a and b and c are not equal to 0, as all values would be 0 and thus no real roots. So now that we're done with that, we sub in the values and we get p as 0.107143 and q as minus 0.0357143. Next, we have to use the derivative, which is equal to q squared over 4 plus p cubed over 27. But before we use the derivative, we have to make sure that 1, p is not equal to 0, otherwise the equation t cubed plus pt plus q equals to 0 becomes t cubed plus q equals to 0. So t is equal to the cube root of q. And then we also have to make sure that q is not equal to 0, otherwise the equation becomes t cubed plus pt equals to 0, and therefore t would be equal to 0 and the plus and minus of square root minus p. And the square root equation would only work when p is below 0. Since we don't have any of these cases, we can continue with calculating our derivative, which gives us 0.000364. Next, there's 3 cases, and that's when the derivative is either equal to 0, above 0, or below 0, and these are the equations we need to use for each situation. In our case, the derivative is above 0, which means we have a new variable u, which is equal to the cube root of minus q over 2 minus the square root of our derivative, which gives us minus 0.10723. And now to calculate the roots, we do u minus p over 3u, which gives us 0.22583. And now we have to convert back from the depressed cubic equation. So since we substituted x is equal to t minus b over 3a, to calculate t, we have to do root minus b over 3a. And if we substitute all the values, we get t as 0.725834. And now if we substitute our x coordinates of our cubic Bezier and our t value, we will get the x coordinate or the distance we chose at the start, which is 2.6. And if we substitute the y coordinates of our cubic Bezier and our t value, we will get the corresponding y value on the graph. So we can check this in Figma very easily. If you make a frame of a width 1000 and height 1000, and then we take the pen tool and we make a quick curve like this, and we take the top point and we do 1000 on the x value and 0 on the y value, and then here we do 0 on the x value and 1000 on the y value, and then for the bottom point we'll do 800, top point we will do 200, then exit out of the pen tool, and then we make a rectangle, give it a stroke, remove the fill, and we give it a width of 600. If we bring this at the top, you will see if you put 81571, it will be right at the point I'll go through another example so you can familiarize yourself. So let's pick this cubic Bezier with the points 0, 0, 0, 0.8, 0.2, 1, and 1, 1. And for the distance, I will select 0.2 and then we add 2 to all coordinates and values, and then we will substitute all of them in the cubic Bezier equation. And if we do all the calculations, we will get A as 0.4, B as 0.6, C as 0, and D as minus 0.2. And then we have the depressed cubic equation, and we also have the warnings, but A is equal to 0.4, so we don't have to worry about that. And most of the time, if you subbed in the right coordinates, you shouldn't have to worry about the warnings, they're just there for the odd instances. So if we substitute all the values, we get P as minus 0.75, Q as minus 0.25, and the derivative gives us the value of 0. And then we obviously have our warning for using the derivative, but P and Q are not equal to 0, and what this means is that we have a different case for our derivative compared to the previous example. So if the derivative is equal to 0, then we have two roots, root 1 which is equal to minus 3q over 2p, and root 2 which is 3q over p, so we get minus 0.5 and 1. But if there are multiple roots, only the positive values below or equal to 1 work, so in this case we will only use the second root which is equal to 1. And now we have to convert from the depressed cubic equation, so t is equal to the root minus b over 3a, and we get t to be equal to 0.5. And if we substitute the values in, we get our distance that we chose and the y equivalent of 2.8. Again, you can check this in Figma yourself, but now let's code all of this. So we're starting off by making a function called calculateValue, and we will add the parameters x1, y1, x2, y2, and duration x. And we will start the function by adding 2 to all the values except the duration x. And next we will create the a, b, c, and d variables where we simplify everything as much as we can. So a will be equal to 1 plus 3 times x1 minus 3 times x2. B will be equal to 6 minus 6 times x1 plus 3 times x2. C will be equal to minus 6 plus 3 times x1. And d will be equal to minus duration x. Next, to see if this works, we will console log out a, b, c, and d, but for this to work we have to call the function, so I will go at the top and do calculate value, and I will put in 0.8 for x1, 0 for y1, 0.8 for x2, 1 for y2, and duration x to 0.6. And as you can see, we get a as 1, b as minus 2.4, c as 2.4, and d as minus 0.6. Now what we do next is work on those cases where using the depressed cubic equation doesn't work. So if math.abs of a is less than 1e minus 8, by the way, what this means is if the absolute value of a is less than 10 to the power of minus 8. And we do this because the computer's calculations aren't always exact like you saw in the console log at the top. Nonetheless, what this means is that we check if a is equal to 0, and if that's true, then we have a quadratic case as I've explained previously. And to turn it from a cubic to a quadratic case, we set a to equal to b, b to equal to c, and c to equal to d. And what we do now is check again if a is equal to 0, but because of the line above, what it actually means is if b is equal to 0, and if so, then it becomes a linear case. So for this we set a equal to b and b equal to c, and for the last time we check if a is equal to 0, which is actually checking if c is equal to 0. And if that's true, it just means there are no roots, so we set roots to an empty array, but now we have to declare roots at the top as well. And next we will write what happens to the roots in the linear case, and for that we will set roots to an array that holds the value of minus b over a. And for the quadratic case, we will create the derivative which is equal to b squared minus 4ac, and so if the derivative is less than 0, then roots is equal to an array with the value of minus b divided by 2a. And next I write a comment explaining that we do this if statement first, because if we had a value of 0.000001, which is essentially 0, it would have returned true for the next if statement, which is if the derivative is above 0. And so if the derivative is above 0, then we will set roots to an array of two values, the first being b minus the square root of the derivative all over 2a, and the second value being b plus the square root of the derivative all over 2a. And then we use else, which checks if the derivative is below 0, which would involve the square root of a negative number, which leads to complex roots, thus no real roots. And so all we've coded right now are the cases where we can't use the depressed cubic equation, so now to use it we will start off by calculating p, which is equal to 3 times ac minus b squared all over 3 times a squared, and then we will also calculate q, which is equal to 2 times b cubed minus 9 times abc plus 27 times a squared times d, all divided by 27 times a cubed. And when we console log p and q out, we get p as 0.48 and q as 0.296. And now that we have p and q, we can calculate the derivative, but first we have to code the cases when p and q are equal to 0. So if p is equal to 0, then the roots would be equal to the cube root of q, and to do this we will use the math.power. However, math.power can't do negative roots, so first we have to check if q is a negative number, and if it is, we will put the negative sign at the beginning and then use math.abs to turn q into a positive value. So again, the reason why we check if q is positive or negative is because math.power cannot do square roots or cube roots using negative values. So as you can see, when q is positive, we remove the negative sign and the math.abs function. And next, if q is equal to 0, we get the roots to be equal to 0 and the plus and minus square root of minus p. However, the square root of a negative number would give an imaginary number, so to avoid that, we check if p is less than 0, otherwise we only get the root 0. So now that we've coded the cases where p and q are 0, we can continue with calculating the derivative, which is equal to q squared divided by 4 plus p cubed divided by 27. And next we have the three cases where the derivative is either equal to 0, is above 0, or is below 0. So first, if the derivative is equal to 0, then the roots are minus 3q divided by 2p and 3q divided by p. Next we have if the derivative is above 0, and if so, we have two new variables, let u and let val, which is equal to minus q divided by 2 minus the square root of the derivative. Next we need to cube root val, and again we use math.power, so we have to check if val is positive or negative. So if val is negative, then u becomes minus math.power of math.absolute val, and we put 1 divided by 3 to make it a cube root. And if val is positive or above 0, then we use the same line but make it positive and keep val as it is. And after that we can calculate the roots, which is equal to u minus p divided by 3u. And then we have the last case where the derivative is below 0, and if so, we will have three new variables. Let u, which is equal to 2 times the square root of p over 3, let t, which is equal to the inverse cos or arc cos of 3 times q divided by u times p, all divided by 3. And let k, which is equal to 2 times math.pi divided by 3. And so we have three roots, which are u times the cos of t, then u times the cos of t minus k, then we have u times the cos of t minus 2 times k. So now if we console log out the roots, we get minus 0.4396, and now we have to convert the roots back from the depressed cubic equation. So we will do so with a for loop in case there are multiple roots. So for let I equals to 0, I is less than roots.length, and I++, we set each root to be equal to the root minus b divided by 3a. And if we console log out roots again, we will get 0.36, and what we will do next is check if the roots we have are between the values 1 and 0, as those are the only real roots. And so we will do roots dot for each root, and what we do next is we check if the root is really close to 1, then the root becomes the exact value of 1, and we will do the same with 0. So again, we use math.absolute for this to work, and 1e minus 8, which is the equivalent to 10 to the power of minus 8. Next, we will add these values to a new array called real roots, so let's declare it before the for each function, and then lastly, we will check if the roots are above or equal to 0 and below or equal to 1, and if so, then we will push the root inside the real roots array. So now if we console log real roots, we will get the same value as we did previously because it is between 0 and 1. And so after this, we will create the variable t, and we will assign it to the first value of real roots. And now we have the x-coordinate equation, which is equal to math.power of 1 minus t to the power of 3 times 2 plus 3 times t times math.power of 1 minus t to the power of 2 times x1 plus 3 times t times 1 minus t times x2 plus math.power of t to the power of 3 times 3 all minus 2. So if we console log out the x coordinate, you will see that we get 0.6, and for the y coordinate, all we have to do is replace x1 and x2 with y1 and y2. So now if we also console log out the y coordinate, we will get 0.296, which is exactly what we want. So lastly, let's return the x and y coordinates, and now if we go at the top, you can play around with different values. Sometimes it doesn't really like values being too fixed, so try adding some decimals. For example, instead of doing 0, do 0.001 if it doesn't work. But now that we're done with our cubic Bezier function, let's go ahead and code the rest. So we're going to start off by selecting our definitions from HTML so we can later on change the standard deviation of the filters inside, and we will also select our container div so we can animate each number inside it properly. We do so through using the document.query selector and selecting the definitions tag and the container class for container div. And next we create a function create odometer that takes two parameters, start val and end val, and we will call the function above and put 0 and 1, 2, 3, 4. Next, inside the function, we create two variables that take the start and ending values and turns them into strings using the toString function. So we end up with the created variables startValString and endValString. Next, we create the variable longerVal and we use it to check if the start or the end value have a larger number of digits. And so we check through an if statement that uses the strings and the function length to tell how many characters or digits the values have. So if the start value has more digits, then the longer value becomes startValString, and the other way around. However, this time we do smaller or equal, and we use equal just so we also have the case where both values have the same number of digits. Next, we create a for loop with our starting point being x is equal to 1, our ending point being the longer value length, so in our case 4 from the value 1, 2, 3, 4, and an increment of 1 for each loop. And inside the for loop, we will create a constant container val div that will be assigned as a new div element, and then we will take container val div and give it two classes, container value, and using string interpolation, we will do container value dash $, curly brackets, and we will put the variable x from our for loop, which will number the second class. And next, we also have to create a filter for each digit, so we will do defs.innerHTML plus equals, so it adds a new filter each time, and instead of writing the whole thing out, we can go to our HTML, copy and paste the filter we've already created. And it should look like so, but now we have to change the ID to a numbered one using string interpolation and the value x again, and we will also reset the standard deviation back to 0, 0. Next, we create the variable amountOfVal, which will calculate how many numbers will be in the container val div. The if statement here doesn't really do anything as it will always return true, but we will reuse it when creating the odometer with strings. Now, to calculate the amount of values, we will compare each two digits between the two numbers. So for example, we will create endValLast character, which is equal to endValString, and we will select the character at the end by doing endValString.length minus x, and if there is no character at that value, we use 0 instead. Then we want to create the second to last character, so we will just copy everything and do endValString.length minus x minus 1. And then we will do the same for the start value, so we will copy everything and replace endVal with startVal. And next, what we will do is combine these two characters, and to do so, we will also use the function parseInt, which will turn the strings into integers. So I will create a new variable endVal character at and do parseInt endVal second last character plus endVal last character. And we will do the same for the start value. Now basically what we've done here is we turned the value 0 and the value 1, 2, 3, 4 into 4 parts, and that's because that's how many times the for loop runs. So if we console log out the endVal character at and the start value character at, you will see that we get the 4 parts of the numbers, and these values will help us determine how many amount of values there are in each container. And now we have two possibilities. When the start value is larger than the end value characters, then the amount of values is equal to the end value characters plus 100 minus the start value characters. So for example, if we have the starting character of 90 and the ending character of 20, then we would have to increment 90 to 100, so 10 values, and then 0 to 20, so 30 values in total. And if the end value character is larger, then we just subtract the end value from the start value. And now that we've calculated the amount of values, we will have to add them. So first we will need a previous value, and we will start with the integer of the starting value's last character. And next we create a for loop with the starting point of I is equal to 1, the ending value of I is less or equal to amount of val plus 1, and with an increment of 1 each time. And inside that we will create a constant value div, which we assign it to be a new div through document.createElement, and then we will give it a class by doing value div.className, and we will set that to value-div. Next we will set the text content, which is equal to the previous value, and now we can append the value div inside the container val div, which we've created at the top of our first for loop. So we do container val div.append value div. And now what we need to do is increment the previous value. So first, if the previous value is equal to 9, then it becomes 0, otherwise we simply increment it instead. And lastly, after the x is smaller or equal to longerVal.length if statement, we will do container div.append container val div. And now if we reload, you will notice that we have these extra zeros. The extra zeros are the values from our JavaScript, so now we can comment out the default values that we've added in our HTML. And now if we use inspect element, you can see that we have all these value divs and container values added automatically. And next, what we will need to do is animate this. So first we will need a transition on our container values. So we will do container val div.style.transition, and we will set it to be affected by all values for 1 second and give it a cubic bezier of 0.90, 0.11, and we will also give it a delay of 0 seconds. And next we have to set a translate value, but in order for it to not be seen as the default value when we reload the page, we will need to use set timeout, and since it's already asynchronous, we can give it a delay of 0. And now we can do container val div.style.translate, and using string interpolation, we will do 0 for x-axis, and for the y-axis we do amount of val times minus 100 inside the $sign curly brackets with a % sign outside it. And the animation seems pretty short, so I will change the transition to 4 seconds instead, and there's one more issue that we need to fix, and that's the container values being reversed. And so to fix this, we will go to our CSS under the container class and do flex direction and set it to row reverse. After this, I will add some parameters to our create odometer function. I will add duration and set a default value of 1 second. Then I will add the first delay and give it a default value of 50 milliseconds. And then I will add the cubic bezier values for the blur, so x1, y1, x2, y2. So now I will go up to where we call the function and put 4 for the duration and 50 milliseconds for the delay. And now I will use these new values to replace what we had for our transition and for our set timeout. And as you can see, if we reload the page, it looks exactly like before. Next, we will target the blur, and that means changing the blur standard deviation, and for that we will use an interval, so we will do new interval is equal to set interval. And inside it we will create a variable final result, which is equal to the calculate function that we've done at the start, and it will take the parameters x1, y1, x2, y2, and x coordinate. And we will increment x coordinate, so first we have to set it to 0 before the interval. And so to increment it, we will first have to check if it's below or equal to 1, and if it is, then we increment it by 0.05, and if it's larger or equal to 1, then we clear the interval and we pass in new interval. And next, what we will do is set the standard deviation of our filter, and so to select the correct filter, we do document.querySelector, and we will select using string interpolation #blurFilter-x, x being from the first for loop we've done. Then we will select again with query selector the class .blurFilterGaussian, which selects the filter tag, and we will set the attribute of standard deviation to 0 for the x-axis, and for the y-axis we will use string interpolation and use the y value of final result by doing final result square brackets 1, and we will multiply it by 40. Next, we need to apply the filter to our container values, so we will do document.querySelector, and using string interpolation we will select container value -x, and after that we will do .style.filter, and we will set that to the string interpolation URL, and inside the parentheses we add #blurFilter-x. And lastly, we have to set how fast the interval runs, so we go after the arrow function and put 20 for 20 milliseconds. So now we can go at the top where we call the create odometer function and add the cubic bezier values 0.90, 0.11, and if we reload the page, we get this, which is not exactly what we want. The first issue is that it became blurry too quickly. We can change this by incrementing x coordinate with smaller values, or by changing the interval time, which I will set as a new parameter in our create odometer function, but I will set it and also give it the default value of 20 because it's a good amount for 60 Hz displays without being too heavy on the CPU. And so now we will increment x coordinate by the interval time divided by the duration times 1000, so it's in milliseconds, and what this equation does is it runs the x coordinate increment for as long as the duration we've set. Now we can change the value 20 to the variable interval time, and this is what it looks like now. As you can see, the second issue is that it remains blurry after the fact, so what we can do to fix this is check if the y coordinate from final result is above or equal to 0.5, and if it is, then we actually want to set its new value to be equal to 1 minus the y coordinate of final result. So it basically goes up to 0.5, then when it hits 0.5 it goes back to 0, and this is pretty much it, but I do want to add a few features. For example, I'm gonna go up to our function and add the new parameter add values. And what we will do with this is go to where we calculated amount of values and do amount of val plus equals to add values times 10. And then I will go back and give it a default value of 0, and where we call the function I will give it a value of 2. So now each container value div has 20 more values. The reason we did this is because before, the first number on the left used to only go from 0 to 1, but now it goes through 21 values, which makes it look more like an odometer. The next parameter I will add is inverse run, which I will set the default to false, but I will set it as true for our callout function. So next we will go to our set timeout, and after the first translate we will check if inverse run is true, and if it is, then we will set the translate to be 0, 0. So we will remove the string interpolation and set it to 0, 0. And then right before the set timeout we will copy the whole line we just wrote, but now we set the default value. And we set it to what we had before, which is 0 with the string interpolation amount to val times minus 100 with a percentage sign outside it. And now the features that we will add are blurring options, so I will add the parameters blur amount with the default value 20, blur height with a default value of false, then I will add blur multiplier, then I will add blur ratio, and lastly we will add blur min cap and blur max cap. So what I will do next is take blur amount and replace the value 40 where we've set our standard deviation. So now I'm going to test it by going to where we call out create odometer, and I will set inverse run back to false and set blur amount to 80. Since we're up here, I'm going to create the variables min blur and max blur inside the function right at the top. But before we use them, we will go to our set timeout and create the case where the variable blur height is true. So if blur height is true, then we set blur amount to be equal to the amount of values for each separate container value div, and we do that by using query selector to select the container values, then we use string interpolation to pass the value x and the functions .children and .length, and lastly we multiply it by blur multiplier. Next I went back to our function's parameters to set the default value of blur multiplier to 1. So now if we go to our function callout, I will set blur height to true, I will keep blur multiplier to 1 and change add values back to 0 as it will be easier to notice. Look at how the transition from 0 to 1 has almost no blur compared to the other values. This is even more obvious when changing blur multiplier to something like 4 or even 20. So now I will undo and work on our blur ratio parameters. So if we go after the for loop where we add our value divs and do if blur ratio is true, then we will have another if statement that checks if min blur is undefined, and if it is undefined or if min blur is larger than the current amount of values times blur multiplier. So if any of those are true, then we set min blur to become the current amount of values times the blur multiplier. And we will do the same with max blur, but we check if it's lesser than amount of val times blur multiplier. Now what this does is it checks to see which container val has the least and the most amount of value divs inside, and we assign it accordingly to min or max blur. So if we console log out min and max blur, and we also have to set blur ratio to something, right now it doesn't matter because we just check if blur ratio is true, but I will put an array of 10 and 100. You will see that it checks each time for the minimum and maximum values. So we have 21 for the minimum and 54 for the maximum. So I'm going to remove the console.log and then continue with our blur ratio. So we're going to go to our blur height if statement and add or blur ratio. And the reason is because blur ratio is basically blur height, but with a minimum and maximum multiplier. So now we're checking if blur ratio is true and that max blur is not equal to min blur. So if both statements are true, then we will do blur amount is equal to the difference between blur amount and min blur, all divided by the difference between max blur and min blur. So what this finds is what percentage is blur amount found between min and max blur. Then we multiply all of that by the blur ratio difference, and then we finally add the minimum value of blur ratio. So again, this is basically blur height, but we apply the blur ratio to the blur height. And then we have the case where max blur is equal to min blur, and if that is true, then blur amount is the value of max blur basically. So what this represents is when there's the same amount of values in each container val div. Next, if blur min cap is true and blur amount is smaller than it, well then we would have to set blur amount to blur min cap so it doesn't go below it, and that's exactly what we do. In the if statement, we also check to see if blur ratio is undefined by adding an exclamation mark in front of it, because blur ratio would already set the minimum and maximum values. Next, we do the same for blur max cap, but obviously we check if blur amount is larger or equal to blur max cap. So if we go to where we call the create odometer function and change our blur ratio to an empty string so it's undefined, we can now set the minimum and maximum blur caps, and I will do 10 and 50, and we can make it a little more obvious by doing 40 and 50 now. So next I will set the blur min and max cap to an empty string, and the last feature I want to add is a duration and a delay increment to each container val div. So I will go to our function and add the parameter duration increment and delay increment. Then I will set both of these to have a default value of 0, and then I will go to where we call out our function and give duration increment a value of 0.1 and delay increment a value of 0 for now. So now let's go before our set timeout where we set our transition, and we will add to our duration in parentheses duration increment multiplied by x, and then we will do the same where we calculate the x coordinate, but make sure to put it in parentheses again as we need to multiply all of that by 1000. And now if we reload the page, you will see the last number to move is 1, but we can make it more obvious by doing 0.5. So now let's work on our delay increment. So first we will set duration increment to 0, and then we will set delay increment to 500, representing 500 milliseconds. And now all we have to do is go to the end of our set timeout and add the first delay increment multiplied by x. Now when we reload the page, it seems a bit too much, but you can lower it to 100 milliseconds. You can also combine delay increment with duration increment, but personally I like just having duration increment set to 0.3 without any delays. And this is it. Well done for making it this far. If you want to create the string variant, you can try it yourself, or you can go to our website and purchase the last part if you wish to do so. And as always, let me know what I should do next.